Hey, hi everyone. I'm not expecting a lot of people today. Like this is more than I expected, honestly. Just because the spring break is next week. So I just want to give you this hour to ask any questions you might have about the current topic. Happy to do any practice problems, just regular general going over something, homework or anything like that. So the hour is yours. Whatever you would like to see. Totally game. Is there anything specific? Mhm. Yeah. Okay. Yes, we can totally talk about that. Do you know what slide number that is from the 8? So what we're looking at with KSP is right, we have BaSO4 solid forming barium 2 plus SO4 2 plus. Okay. So when we're talking about KSP, right, we're talking about the equilibrium of the solubility product, right? So the solubility product is how much of that ion is in solution at equilibrium. So if you think about it that way, then what KSP means might help you with some of these questions moving forward, because you're looking at what does it mean or how does it take this insoluble salt to make it soluble, just a little bit amount. What is that causing in the reaction? Okay, so if we know the KSP is 1.1 times 10 to the negative 10. So what contributes to the KSP when we talk about an insoluble salt? The left or the right-hand side, or both? Like, how would I write the equilibrium expression for KSP? Just the right side, right? It's just your products. We only care about our aqueous component still. We don't care about the solid. So your KSP is equal to the concentration of your barium ion times the concentration of your sulfate ion. Okay, so that's the only thing that's contributing to that value that we're given. So if we were to add water, what does that do to our solution? It dilutes it, right? When we immediately add water to our solution, we're immediately diluting the concentration. So did we increase or decrease that K value? We decreased it, right? Because now we have smaller numbers, right? So this would make concentration smaller. So, right, even if we said we had, it was 1 times 1, right, then KSP is 1. But now we diluted it, so now we have 0.5 and 0.5. So now we have our KSP is 0.25, right? But that's not actually KSP. This is now Q, right? Once we dilute it, we changed our system. What happens to Q? Q becomes less than K. And what does that mean we have to do in order to reach equilibrium? Yeah, we have to make more products, right? So we have to go towards products. So this adding water means that you're causing more ions to dissolve in solution, right? So this would cause more salt to dissolve, making more ions in solution. Okay, does that make sense why adding water does that? Okay. Right. It's now playing into Le Chatelier's principle of like, what happened? We made a disruption to equilibrium. So now we have to question if we're still at equilibrium or if we're someplace else now. Okay. Any other questions on just adding water? Cool. Right. So then B was adding BaCl2 solid. And what's going to happen to BaCl2 solid in solution? And does it dissociate a lot or does it dissociate a little bit? How would we check that?
Yeah, it dissociates into both BA.
Right, so if we looked at the old exam, so I can just find the answer or the formula sheet you're given. Right, if we look at our solubility table, chlorine is usually soluble. With the exceptions of silver, mercury, and lead. So is barium one of the three exceptions? No, right? So if anything is with chlorine, it's going to break apart. So this would dissociate into barium 2+ into Cl-. So that's going to increase the barium concentration and increase the chlorine concentration. Do we have any common ions between the ions in barium chloride and the ions in barium sulfate? Barium is going to be, right, a contributor to the system. So if we now look at our KSP or we look at our original dissociation, we've now increased the concentration of barium 2+. So if we solve for Q, right, if we're just giving ourselves random values here, let's say now we have 2 times 1, right? We said our original was 1 times 1 to give us 1. But now we've increased our concentration to 2. So what does Q become? Q equals 2. And so now how does Q compare to K? Q is greater than K. And so, since Q is greater than K, which way are we going? To the left, towards reactants. So it's actually going to take some of those sulfate ions in solution and form more barium sulfate solid because we have an increase in our barium ions from this salt being dissolved. Does that make sense? Yeah, okay. Okay. So then similarly, look at this. If we were to add potassium sulfate this time, we check our solubility chart and this now becomes K+ and SO4 2-. So what's going to happen when we add potassium sulfate to solution? Right, it's gonna do the same thing that happened in B, but now we're just increasing a different ion. So now we're increasing the sulfate. What happens to Q? Become greater than or less than K. Becomes greater than K, so we're gonna form more reactants. So this is going to create more solid, take ions out of solution. That's because there's a common ion between the salt that's already dissolved and then the new salt that's being added. Hey, questions on B and C? Does that make sense? Okay, so then the different one is D. This time we're adding sodium chloride. What happens to sodium chloride in solution? That breaks into Na plus and Cl minus. Now, do we have any common ions with our original salt? Nope. So what is that going to do to K? Nothing, right? We're not increasing the concentration of anything. We're not decreasing the concentration of anything. This has no effect because there's no common ion. So equilibrium, right? Therefore, equilibrium is not affected. We'll call it that. Affected. Impact. Equilibrium is not changed. Q equals K. Right, does that help that slide? Okay. Right, so anytime you just want to see, you always want to check your solubility chart, make sure it actually is dissolving. And if there's any sort of common ion, then it's going to have some sort of impact on it. And even just since these are all insoluble salts, just the slightest change would always have an effect on it. Yep. Any other questions on this material? Yes, so like if you're just setting up an insoluble salt, you have a solid, right? And that solid is going to go into your beaker. Right, so most of your solid is going to end up on the bottom of your beaker, and then you're going to have water here. If you were to stir that or agitate it, little particles are going to pop out. So right after stir, and then you'll still have your beaker. You'll still have your solid, but now you'll have just a couple particles that have formed in solution. And this is because that equilibrium has to form, right? If you just have the solid, it's like looking at an ice table. Where when you just put your solid in, do we have any products when we first put that solid in solution? No, right? So that becomes that our initial for these ions is 0. So what does Q equal then? It would be 0, right? So if Q is equal to 0 and K is equal to 1.1 times 10 to the negative 10th, what is Q in comparison to K? It's less than, right? Q is less than K. So we have to form or go towards products, and we have to form some of those products in order to saturate the solution, right? So that's just initial solution being formed. And it'll always form based off of the equilibrium. So if we were to complete this ice table, what is going to be our change for barium and our change for the sulfate ion? It'll be positive. Is it X, 2X? It's just X, right? It's just X for both of them. So equilibrium is X. So since we're given KSP, we could solve for what that concentration of the barium and the sulfate ions would be. Right, it's just 1.1 times 10 to the negative 10th equal to X times X. So it just becomes X squared. And then you can just square root for both of them. I think it's like 5.55. Yep. So this X becomes 1.05 times 10 to the negative 5. So that would be the concentration of both of them at equilibrium. And if you have that concentration, you can consider it saturated. Anything else? Right, so if we looked back at our 4 conditions of changing or adding stuff to a solution, right, which one forms more precipitate? I'll include D. Right, B would. And also C, right? Since Q is greater than K, we're forming more reactants, which is forming more solid. So it's not going to be a lot, but it does form more of that initial solid compound. So if you see any of those types of questions, if you're forming more reactants, you're always forming more solid. Mm-hmm.
Because like K was really small, or because like was it because 0.1 is, I don't know, why did we think?
Yeah. Do you know what slide number that was?
Mine, because after the pastures with the yellow red from
Okay. Oh, yep. Okay. So, right. So we found what the molar solubility of would be, and then we said that for, right, 0.1 molar Na2SO4. Right, this is saying that in solution, this will break apart into 2 Na plus and SO4 2 minus. So what molar concentrations of each of these do we have of the ions? We have 0.1 molar of the sulfate, and how much of the sodium? 0.2, right? Because we have twice as many sodium ions. Yep. So we'll have 0.2 molar. It doesn't really matter, but just to remember what coefficients mean and stuff. Right. So if we're looking at 0.1 molar sulfate ions, that means when we start in our solution, we have barium sulfate. Oops. This time when we do our ice table, do we start with 0 and 0 as our initial concentrations? right, we do have some sulfate. So we have 0 barium, but now we have 0.1 molar sulfate ions right off the bat. So what does that mean for Q and K? What do we do? Or what does our change turn into? It would still be positive, right? Because we have no barium, we still need to form some barium. So this is still going to be plus X. This is still plus X. This is X and then 0.1 plus X. We can call the plus X for the sulfate ion negligible because of a couple of reasons. One, KSP is 1.1 times 10 to the negative 10th. If your equilibrium has an exponent of 10 to the negative 5, I'm going to say, or less, meaning it gets a larger negative number, right? So 10 to the negative 6, 10 to the negative 7, so on and so forth, like a more positive actual exponent value, but a smaller number overall. That means that your change is going to be very, very small, or you have very, very little concentration at the beginning. So because not a lot is going to be formed, most of that concentration of the sulfate ion in solution is going to look like 0.1, right? If we're going to take significant figures into consideration, it would probably just end up back at 0.1.
Is it basically in water or for the, like, how does it relate to what it's in different solid?
So there's still saying, since it's 0.1 molar sodium sulfate, it's saying that the sodium sulfate is dissolved in water. So you have a solution of 0.1 molar sodium sulfate that you're dropping that barium sulfate into. Yep. So, right, we already have, we have our beaker of we have our solid of barium sulfate, but this time our beaker, instead of being water here, this has Na plus ions, but it's the same because this is still dissolved in water. It's not like dissolved in methanol or some organic solvent, right? It's still dissolved in water for the ions there.
So it first to dissolve sodium sulfate in water?
Yes. 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 Yep. So they made a solution of the sodium sulfate first. That's 0.1 molar. And then they put the barium sulfate in it.
If it were in a different solvent, the KSP would be different?
Yes. Yeah. Because then it's like, then your likes don't dissolve likes as much or something like that, right?
Reaction. Like it's the product's concentration.
Yeah, it's the solubility product. So it's, right, solubility is how much something can be dissolved, or your concentration is another word for solubility. Product multiplication, right? So you're taking the solubility or the concentration of your ions and you are multiplying them at equilibrium.
So
That'll change depending on, it has the same rules as all the other Ks, on temperature, on concentration, on all of that stuff that way. So, and it'll change depending on the reaction that you're working with. But because we already have this sodium sulfate ion already dissolved in water, it's starting off like that. That's why we have 0.1 molar in the beginning for our sodium or for our sulfate ion, unlike the barium sulfate where it was just being dissolved in straight up water, right? This is being dissolved in pure water. This one's being dissolved in sodium sulfate water. So the equilibrium is still the same. The value that we're going to get for X will be different. Well, let's keep going with it. maybe seeing the actual numbers will make it a little bit more sense, right? So at equilibrium, we have x in 0.1 plus x, but that plus x is going to be really, really small, right? So KSP here is still 1.1 times 10 to the negative 10. Because, right, equilibrium is dependent on temperature. We didn't change the temperature. It's still equaling this. We just have varying concentrations of those ions in solution. So this is still concentration of barium 2 plus and SO4 2 minus. At equilibrium, this is saying that 1.1 times 10 to the negative 10th is equal to x times 0.1 plus x. But we can say that this goes to 0 and is negligible because our KSP is so small. And we have so much excess sodium sulfate, or so much excess sulfate ions. Because the other time that you can assume that the X will be negligible is if you have a magnitude difference of 3 or more between your KSP exponent and your initial concentration exponent. So 0.1 is actually 1 times 10 to the negative 1. And our KSP is 1.1 times 10 to the negative 10th. So there are 9 magnitudes of difference between -1 and -10. So since that is such a large range, we can assume that any change is going to be negligible there. Okay. Correct, right? Because we do need to form some of that X. It's not going to stay 0. A little bit is going to form, but it's not going to be enough to make a 0.1 change that much. Right, and you'll see that when we do solve for X. So
disregard X.
Mhm. We can try. It would then require you to use the quadratic formula because you're going to get an X squared. But we can plug that into the quadratic formula and see if there's too big of it. I can just plug it into the computer one and we can do it. Usually it doesn't. So if we do neglect it, then it becomes 0.1x, and then you can just divide by 0.1. Right, so x becomes 1.1 times 10 to the negative 9th. Okay. So at equilibrium, what does this mean? That means that we have is equal to x, which is 1.1 times 10 to the negative 9th. And the sulfate ion is 0.1 plus x, which is 0.1, 1, 2, 3, 4, 5, 6, 7, 8, 9. Right, something like, I think it's that many zeros. But either way, a lot of zeros before you see that one. So if we were to round that, what would you round it to? You would round it to 0.1. So at equilibrium, this still looks like 0.1, which is why we can neglect it, because even though there's still a little bit more at equilibrium, we can't really tell that. It's still we probably wouldn't be able to detect it, honestly. So it's still 0.1 because the change is so small. But we do form some of that barium complex, right? We do have some of that barium ion, and if we were to solve for the KSP, it would be 1.1 times 10 to the negative 9 times 0.1, which would get us back to 1.1 times 10 to the negative 10. Right, so it still matches the KSP from when we didn't have the sulfate ions in the beginning, but now our concentrations of the two, or the ratios of the two, are different because we started off with more sulfate ion than we did barium ion. Does that make a little bit more sense? Okay. Sometimes it's easier to see the math and the numbers actually work out. All right, and then if we were to plug this into the quadratic formula, what would that be? That would be x squared plus 0.1x minus 1.1 times 10 to the negative 10. We'll do a quick little quadratic calculator. Okay, so it does not change it, like literally at all. So, um, so that's why the, in this case, this one doesn't really change it at all. So that's why you can just assume that it's negligible. Some of them, they do factor a little bit. So there's a way to check it, but I think most of the time she'll make you able to assume that you can neglect it. Yeah. Not neglect, it still matters. We don't want to make it hurt its feelings. Yeah, of course. Any other questions on KSP? Is that the iClicker problem? Or the AGCL?
Yeah.
Yes. We have if 50 milliliters of 0.02 molar calcium is mixed with 50 milliliters of 0.0150 molar sulfate, will calcium sulfate precipitate from solution? Okay. So there's two things you have to do for this problem. Does not matter which one you do first. Do you know either step that has to be done? Or have any ideas of how you want to start it? Right, we can write QSP or KSP, excuse me, for the calcium sulfate. So, right, we're looking for calcium sulfate. That's going to be Ca is 2 plus and sulfate is 2 minus. So it's going to be 1 to 1. So calcium sulfate. And that forms a calcium 2 plus ion, and it forms a sulfate ion. Okay, what do you think is the next thing we have to do? Or what's another thing that we might have to do? Might necessarily be the next thing. Right, so we do need to figure out where we are, right? We have some solution of calcium, we have some solution of sulfate ions. We need to figure out what are we starting with? Where are we, right? We don't know. So how would we find the concentration of these ions? What are we doing when we're combining them? So we're doing a dilution, right? We have 50 milliliters of 0.02 molar calcium, and we're adding that to 50 milliliters of the sulfate ion. So what is our total volume after we combine them? 100 milliliters. Do you know what our final concentration of calcium is? No, but we can solve for it, right? This is just M1V1 is equal to M2V2. So our final concentration of calcium is 0.01 molar calcium 2 plus ions. Can we find the concentration of our sulfate ions? We have those concentration of calcium plus ions and sulfate ions. How do we check to know if a precipitate is going to form? Right, we compare Q and K. And how are we going to compare Q and K? How do we set up Q? That's just our calcium ion times the concentration of our sulfate ion. Do we know the concentrations of both of those? We do. So we have 0.01 molar and we have 0.0075 molar. And we end up with 7.5 times 10 to the negative 5 as Q. How does that compare to K? It's greater than, right? K, this looks like a 7, 2, we'll change that. So K is equal to 4.9 times 10 to the negative 5. So in this case, Q is greater than K. So what do we form? We form the reactants, which happens to be our solid. So does a precipitate form? Yeah, yep. Yes, precipitate forms. Yeah, okay. There's a way that you could check this as well. Using the KSP value, right? You know, you have calcium 2 plus and sulfate. So if you did your ice table, it would end up as x squared. So if you solve for x, then you get x is equal to 0.007. as the X value, right? So that's the concentration at equilibrium. When we solved our dilutions, we got 0.1 molar, oops. When we solved for our dilutions, we got 0.1 molar and we got 0.0075, right? So those are both greater than the solubility from the solubility product from the original KSP. So since they're both greater, we know then as well that it has to form more products because we have to reduce that to get back to equilibrium. Okay, does that make sense how you would check it? Yeah. I know this is a little confusing, right? Yep. I know I try to give visual cues for me as much as possible, just so I'm like, if I'm taking a test, I'm like, okay, yeah, this is what I do. And this is like, even still to this day, I'm doing problems and I still use all the visual cues as much as possible. So if you can find those for yourself, it's very helpful. Yep. Is there any other questions you had? Okay. Yeah, I don't expect the week before spring break to be very student heavy. Yeah. Yeah. I think just because there's a lot to do and there's a lot of steps to each problem, you have to like recognize what the question is asking, wanting you to do, so you do it right the first time. So I think the more you practice, the more you see that kind of wording, and that helps a lot. Yeah, absolutely. Have a nice break. Thank you.